The essence of abstractions is preserving information that is relevant in a given context, and forgetting information that is irrelevant in that context. John V. Guttig. In computer science, abstraction is a technique for managing complexity of computer systems. It works by establishing a level of complexity on which a person interacts with the system, suppressing the more complex details below the current level. The programmer works with an idealized interface and can add additional levels of functionality that would otherwise be too complex to handle. For example, a programmer writing code that involves numerical operations may not be interested in the way numbers are represented in the underlying hardware. In addition, a task of sending an email message across continents would be extremely complex if you start with a piece of optic cable and basic hardware components. By using layers of complexity that have been created to abstract away the physical cables, network layout and presenting the programmer with a virtual data channel, this task is manageable. Abstraction can apply to control or to data. Control abstraction is the abstraction of actions, while data abstraction is that of data structures. Control abstraction involves the use of subprograms and related concepts, control flows. Data abstraction allows handling data bits in meaningful ways. For example, it is the basic motivation behind data type. One can view the notion of an object as a way to combine abstractions of data and code. The same abstract definition can be used as a common interface for a family of objects with different implementations and behaviors but which share the same meaning. The inheritance mechanism in object-oriented programming can be used to define an abstract class as the common interface. The recommendation that programmers use abstractions whenever suitable in order to avoid duplication is known as the abstraction principle. The requirement that a programming language provide suitable abstractions is also called the abstraction principle. Rationale. Computing mostly operates independently of the concrete world. The hardware implements a model of computation that is interchangeable with others. The software is structured in architectures to enable humans to create the enormous systems by concentration on a few issues at a time. These architectures are made of specific choices of abstractions. Greenspun's 10th rule is an aphorism on how such an architecture is both inevitable and complex. A central form of abstraction in computing is language abstraction. New artificial languages are developed to express specific aspects of a system. Modeling languages help in planning. Computer languages can be processed with a computer. An example of this abstraction process is the generational development of programming languages from the machine language to the assembly language, and the high-level language. Each stage can be used as a stepping stone for the next stage. The language abstraction continues, for example, in scripting languages and domain-specific programming languages. Within a programming language, some features let the programmer create new abstractions. These include subroutines, modules, polymorphism, and software components. Some other abstractions such as software design patterns and architectural styles remain invisible to a programming language and operate only in the design of a system. Some abstractions try to limit the breadth of concepts a programmer needs by completely hiding the abstractions that in turn are built on. The software engineer and writer Joel Spolsky has criticized these efforts by claiming that all abstractions are leaky, that they can never completely hide the details below. However, this does not negate the usefulness of abstraction. Some abstractions are designed to interoperate with others. For example, a programming language may contain a foreign function interface for making calls to the lower-level language. Data abstraction is the separation between the specification of data object and its implementation. Language features. Programming languages. Different programming languages provide different types of abstraction, depending on the intended applications for the language. For example, in object-oriented programming languages such as C++, Object Pascal, or Java, The concept of abstraction has itself become a declarative statement, using the keywords virtual or abstract and interface. After such a declaration, it is the responsibility of the programmer to implement a class to instantiate the object of the declaration. Functional programming languages commonly exhibit abstractions related to functions, such as lambda abstractions, higher-order functions. Bracket abstraction. Modern Lisps such as Clewett, Scheme and Common Lisp support macro systems to allow syntactic abstraction. This allows a Lisp programmer to eliminate boilerplate code, abstract away tedious function call sequences, implement new control flow structures, implement or even build domain-specific languages, which allow domain-specific concepts to be expressed in some optimized way. A consequence of syntactic abstraction is also that in any Lisp dialect, and in fact almost any programming language, can, in principle, be implemented in any modern Lisp with significantly reduced effort when compared to more traditional programming languages such as Python, C or Java. Specification methods. Analysts have developed various methods to formally specify software systems. Some known methods include abstract model-based method, algebraic techniques, process-based techniques, trace-based techniques, knowledge-based techniques. Specification languages. Specification languages generally rely on abstractions of one kind or another. Since specifications are typically defined earlier in a project than an eventual implementation, the UML specification language, for example, allows the definition of abstract classes, which remain abstract during the architecture and specification phase of the project. Control abstraction. Programming languages offer control abstraction as one of the main purposes of their use. Computer machines understand operations at the very low level, such as moving some bits from one location of the memory to another location and producing the sum of two sequences of bits. Programming languages allow this to be done in the higher level. For example, consider this statement written in a Pascal-like fashion. Equals *5 to a human. This seems a fairly simple and obvious calculation. However, the low-level steps necessary to carry out this evaluation, and return the value 15, and then assign that value to the variable are actually quite subtle and complex. The values need to be converted to binary representation and the calculations decomposed into assembly instructions. Finally, assigning the resulting value of 15 to the variable labeled so that can be used later, involves additional, behind-the-scenes steps of looking up a variable's label and the resultant location in physical or virtual memory, storing the binary representation of 15 to that memory location, etc. Without control abstraction, a programmer would need to specify all the register, binary level steps each time they simply wanted to add or multiply a couple of numbers and assign the result to a variable. Such duplication of effort has two serious negative consequences. It forces the programmer to constantly repeat fairly common tasks every time a similar operation is needed. It forces the programmer to program for the particular hardware and instruction set. Structured programming. Structured programming involves the splitting of complex program tasks into smaller pieces with clear flow control in interfaces between components, with reduction of the complexity potential for side effects. In a simple program, this may aim to ensure that loops have single or obvious exit points and to have single exit points from functions and procedures. In a larger system, it may involve breaking down complex tasks into many different modules. Consider a system which handles payroll on ships and its shore officers. The uppermost level may feature a menu of typical end-user operations. Within that could be standalone executables or libraries for tasks such as signing on and off employees or printing checks. Within each of those standalone components there could be many different source files. each containing the program code to handle a part of the problem, with only selected interfaces available to other parts of the program. A sign-on program could have source files for each data entry screen and the database interface. Either the database or the payroll application also has to initiate the process of exchanging data between ship and shore, and that data transfer task will often contain many other components. These layers produce the effect of isolating the implementation details of one component and its assorted internal methods from the others. Object-oriented programming embraces and extends this concept. Data abstraction. Data abstraction enforces a clear separation between the abstract properties of a data type and the concrete details of its implementation. The abstract properties are those that are visible to client code that makes use of the data type, the interface to the data type, while the concrete implementation is kept entirely private, and indeed can change, for example to incorporate efficiency improvements over time. The idea is that such changes are not supposed to have any impact on client code, since they involve no difference in the abstract behavior. For example, one could define an abstract data type called lookup table which uniquely associates keys with values, and in which values may be retrieved by specifying their corresponding keys. Such a lookup table may be implemented in various ways, as a hash table, a binary search tree, or even a simple linear list of pairs. As far as client code is concerned, the abstract properties of the type are the same in each case. Of course, this all relies on getting the details of the interface right in the first place, since any changes there can have major impacts on client code. As one way to look at this, the interface forms a contract on agreed behavior between the data type and client code. Anything not spelled out in the contract is subject to change without notice. Languages that implement data abstraction include Ada and Modula2. Object-oriented languages are commonly claimed to offer data abstraction. However, their inheritance concept tends to put information in the interface that more properly belongs in the implementation. Thus, changes to such information ends up impacting client code, leading directly to the fragile binary interface problem. Abstraction in object-oriented programming. In object-oriented programming theory, abstraction involves the facility to define objects that represent abstract actors that can perform work, report on and change their state, and communicate with other objects in the system. The term encapsulation refers to the hiding of state details, but extending the concept of data type from earlier programming languages to associate behavior most strongly with the data, and standardizing the way that different data types interact, is the beginning of abstraction. When abstraction proceeds into the operations defined, enabling objects of different types to be substituted, it is called polymorphism. When it proceeds in the opposite direction, inside the types or classes, structuring them to simplify a complex set of relationships, it is called delegation or inheritance. Various object-oriented programming languages offer similar facilities for abstraction, all to support a general strategy of polymorphism in object-oriented programming, which includes the substitution of one type for another in the same or similar role. Although not as generally supported, a configuration or image or package may predetermine a great many of these bindings at compile time, link time, or load time. This would leave only a minimum of such bindings to change at runtime. Common Lisp object system or self, for example, feature less of a class instance distinction and more use of delegation for polymorphism. Individual objects and functions are abstracted more flexibly to better fit with a shared functional heritage from Lisp. C++ exemplifies another extreme. It relies heavily on templates and overloading and other static bindings at compile time, which in turn has certain flexibility problems. Although these examples offer alternate strategies for achieving the same abstraction, they do not fundamentally alter the need to support abstract nouns in code. All programming relies on an ability to abstract verbs as functions, nouns as data structures, and either as processes. Consider for example a sample Java fragment to represent some common farm animals, to a level of abstraction suitable to model simple aspects of their hunger and feeding. It defines an animal class to represent both the state of the animal and its functions. Public class animal extends living thing, private location lock, private double energy reserves, public boolean ish hungry, consume food, energy reserves plus equals food dot get calories, move to new location this dot lock equals location. With the above definition, one could create objects of type animal and call their methods like this. The pig equals new animal, if the pig.eat, if the cow.eat, the cow.movito. In the above example, the class animal is an abstraction used in place of an actual animal. Living thing is a further abstraction of animal. If one requires a more differentiated hierarchy of animals to differentiate, say, those who provide milk from those who provide nothing except meat at the end of their lives, that is an intermediary level of abstraction. Probably dairy animal who would eat foods suitable to giving good milk, and meat animal who would eat foods to give the best meat quality. Such an abstraction could remove the need for the application coder to specify the type of food, so he could concentrate instead on the feeding schedule. The two classes could be related using inheritance or stand alone, and the programmer could define varying degrees of polymorphism between the two types. These facilities tend to vary drastically between languages, but in general each can achieve anything that is possible with any of the others. A great many operation overloads, data type by data type, can have the same effect at compile time as any degree of inheritance or other means to achieve polymorphism. The class notation is simply a coder's convenience. Object-oriented design decisions regarding what to abstract and what to keep under the control of the coder become the major concern of object-oriented design and domain analysis. Actually determining the relevant relationships in the real world is the concern of object-oriented analysis or legacy analysis. In general, to determine appropriate abstraction, one must make many small decisions about scope, determine what other systems one must cooperate with, then perform a detailed object-oriented analysis which is expressed within project time and budget constraints as an object-oriented design. In our simple example, the domain is the barnyard, the live pigs and cows and their eating habits are the legacy constraints. The detailed analysis is that coders must have the flexibility to feed the animals what is available, and thus there is no reason to code the type of food into the class itself, and the design is a single simple animal class of which pigs and cows are instances with the same functions. A decision to differentiate dairy animal would change the detailed analysis, but the domain and legacy analysis would be unchanged. Thus, it is entirely under the control of the programmer, and we refer to abstraction in object-oriented programming as distinct from abstraction in domain or legacy analysis. Mechanism in object-oriented programming can be used to define an abstract class as the common interface. The recommendation that programmers use abstractions whenever suitable in order to avoid duplication is known as the abstraction principle. The requirement that a programming language provide suitable abstractions is also called the abstraction principle. Rationale. Computing mostly operates independently of the hardware components, by using layers of complexity that have been created to abstract away the physical cables, network layout and presenting the programmer with a virtual data channel. This task is manageable. Abstraction can apply to control or to data. Control abstraction is the abstraction of actions, while data abstraction is that of data structures. Control abstraction involves the use of subprograms and related concepts, control flows. Data abstraction allows handling data bits in meaningful ways. For example, it is the basic motivation behind data type. One can view the notion of an object as a way to combine abstractions of data and code. The same abstract definition can be used as a common interface for a family of objects with different implementations and behaviors but which share the same meaning. The inheritance the essence of abstractions is preserving information that is relevant in a given context, and forgetting information that is irrelevant in that context. John V. Guttig. In computer science, abstraction is a technique for managing complexity of computer systems. It works by establishing a level of complexity on which a person interacts with the system, suppressing the more complex details below the current level. The programmer works with an idealized interface and can add additional levels of functionality that would otherwise be too complex to handle. For example, a programmer writing code that involves numerical operations may not be interested in the way numbers are represented in the underlying hardware. In addition, a task of sending an email message across continents would be extremely complex if you start with a piece of optic cable and basic hardware.